Is it visible on the whiteboard?
Yes, sir.
Yes, sir. Whiteboard is visible.
Then very good. So it is very Hey, Prashant, I am in the class. Okay. Okay, let's really start it. Uh, uh, Last class we are discussing about the evolution of IC. Uh, as I told that we have started from the 1995 when the electrons evolved, and how the vacuum diode has invented. Then vacuum diode is used as both diode and triode, and further the vacuum triode is used as an amplifier, and further it is it is employed to develop a computer systems which is a very large scale, right, which is a very large size. To minimize this large size computing systems with the very smaller one, so silicon devices is invented, and 1947 then 1950 it is the first transistor is uh, uh, realized on the silicon. Then integrated circuit concept came up, and then IC is evolved. Then IC, the evolution of IC, as I was talking, that it is started from the single single transistor integrated circuit, then small scale integration circuit, then large scale integration circuit, then it has come up the VLSI, right? So this VLSI, the term, the V, एक minute, something wrong. So VLSI, when talking on the VLSI, what is a VLSI? Very large scale integrations, very large scale integration. Okay, very large scale integration. The acronym of the VLSI is very large scale integrations. The definition is that this is the definitions you can write it. We will start with the definition and try to understand VLSI. Uh, uh, Definition is that this is the integration of integration of millions of transistors million of transistors so I don't know how it will go. Millions of integration of integration of millions of transistors on monolithic text is issue. monolithic monolithic chip. Oh, now it is okay. Monolithic. Is that mean? Monolithic chip. So it is an integration. You see, I think handwriting. I'm not sure whether you are able to get it or not. But if you're not getting, just to tell me. Okay. So this is called integration of millions of transistors on monolithic chip. That monolithic is a Greek word. Mono means single, and lithic means stone. Okay, single stone chip. Stone means it is made of the silicon, right? So it is a integration of millions of transistors on a silicon chip. Okay, on a single silicon chip. This is called a definitions, right? And if you look at the how to move forward. Okay. Now, when you're talking about it is a integration of millions of transistors on monolithic chip, right? So if you say that integration of millions of transistors on monolithic chip means that integration of it is called a transistors, or sometimes people talk about devices, or sometimes it is people talk about components. Okay, so when you put into a silicon chip, silicon stone or silicon chip, that is a single silicon chip, then you can say that there are many steps you have to follow to get your silicon chip. So if you look at that silicon chip means that VLSI. What is happening here? Yeah. So look at a VLSI chip means that the silicon chip, it is nothing but your VLSI. Okay, so okay, so this VLSI chip, you can realize on silicons. To realize on the silicon, you have to follow some steps, and the first step is called design step. Design step means that you have to go for the design of transistors and its integrations to form a circuit. So that is called a design step. So once it is done in the design step, then you have to realize on your silicon chip, and that is called your realization of the transistors on a silicon. That is called your fabrication step. So one is a design step, another is your fabrication steps. So in addition to that, when you talk about design steps means you have to design your circuit, design your transistors, design your circuits means that is your transistors with interconnections. So find out a appropriate circuit for your applications. Then those circuits, I mean your transistors and uh, interconnections, you have to realize on the silicon. That step is known as a fabrication step. That is known as your fabrication step. Basically, in VLSI terminology, the design part, it is called your VLSI design. Okay, VLSI design, and the fabrication part, the generally called VLSI technology. VLSI technology. Okay, VLSI technology is a technique or methods you have to study. The how you can realize your how you realize your electronic circuit on silicon. So all the methods, all the techniques you have to study on the VLSI technology part. So that the let will come up. This out of these two steps. Basically, when you will go to the design part, any circuit you have to design it, that you have to verify it, right? You have to validate it. And once you do the verification or validation of your design, then 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 after you will go to the your fabrication step, where you can realize your silicon, where you can realize your circuit on your silicon. So once you realize on the silicon, and when you got your VLSI chip, then you have to test it, right? So there are other dimensions of this topic is called your mm, you can say, एक minute. Yes. So other part of your circuit is your other part of this topic is your uh, 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 verification, or you can say validation, or you can go for the testing. Basically, verification or validation is coming under the design part. So different steps will have a different type of verification and validation methods you have to do. We will discuss those also. And the testing is, you have to do the testing on your physical silicon chip. When you realize your when you will get your physical silicon chip, then you have to test it whether it is working or not, right? So basically the verification and validation or testing you have to do in addition to your design steps and the fabrication steps. So broadly you can say the whole topic of the VLSI is summarized to in broadly that VLSI design, VLSI technology, and IC verifications or validation or testing, right? So I mean design, verification, and fabrication. So broadly you can say that you will get your three steps, three broad uh, topics. That is your design, that is called your design or VLSI design, VLSI design, and you can say that verifications, VLSI verifications, that is called IC verifications, VLSI verifications. Okay, or you can say that validation, and the third one is your VLSI testing, VLSI testing. VLSI testing. So out of this topic, mostly we will cover in our this course in EE 309. That will cover mostly on the VLSI design. Major portions will cover on the VLSI design, and also some part of the verifications, particularly functional verification and timing verifications or validations. We will do that. That methods I will talk about it, and we will do the experiment also. And in the end, I may be exposure. We will not cover uh, because VLS testing is another topic. So another topic means another like course. But I will exposure to you. What is the fundamentals of the VLSI testing. So okay, so these portions we will cover it. VLSI design, mostly we will cover the VLSI design. Major part of that this VLSI we will cover the design, and I will introduce the verification again. Verification validation is a another course where you but I will exposure most of them, and VLSI testing. So design, verification, testing we will cover in this subject in this course, particularly E309. And of course we will do some laboratory component, laboratory part under design and verifications in subject EE311. So when you're talking about the VLSI design, come to the VLSI design part. If you come to the VLSI design part, then you know in the VLSI design part, basically we will study the topic that is called a VLSI. We will study VLSI design methodologies. Okay, VLSI design methodologies. So if you look at the VLSI design methodologies, there are basically two methods. One is called a full custom, and another is called a semi-custom. Semi-custom design method. Semi-custom design and full custom design. So try to understand this full custom design and semi-custom design. So in full custom design, you have to customize your design to the specifications. So what is your desired specifications? You have to customize it. Means you have to satisfy your design, or you have to satisfy your design and final chip with respect to your required specifications. Right, whatever the specifications. So suppose your circuit should operate at 100 megahertz, then you have to design your circuit such that it should give you the 100 megahertz. Or if you look at that, if it is first okay, before going to that, I didn't talk about another very introduction part, that is your objective of the VLSI, right? Objective, though I have already discussed, but I didn't make it summarize. So objective of VLSI. Okay, can you tell what is the objective of the VLSI? I already told that VLSI, the objective of VLSI is that to miniaturize or to have a smaller size chip. Okay, and second is that it should have a higher performance higher performance in terms of speed, higher performance in terms of in terms of speed, means that speed of operation should be higher. And third is that it should consume a low power, should consume low power, right? So this is the three objectives. Of course, these are the three challenges you can say that, but objective is that your chip should be smaller size, and it should have a better performance or a higher performance in terms of the speed, means speed should be higher, and it should consume the low power. Of course, this is depending upon your applications you need it. Sometimes if you look at the biomedical applications with the low frequency signals, there is no need to have a high speed performance circuit. Okay, high performance in terms of speed for your circuit, right? So lower speed circuits also will work for the low frequency operations, particularly the biomedical signal processing. But other side, if you look at the communication systems applications where you have to operate at a gigahertz range, so you need a megahertz or gigahertz, then your circuit should be work at that range. So speed of operation should be faster so that it will be suitable for the communications applications. Okay, uh, communication applications. Similarly, if you look at the smaller size, so if you look at the size, that sometimes that depends depending upon the applications. Sometimes the size is not that much constraints or that much needed, but some applications you need a very small size chips. Of course, smaller size is always it is a desirable, but not always it is required, because if you go with the smaller size, then you may have to compromise with the other two parameters, because all this size, speed and power you cannot optimize all together. You cannot achieve all together all these three parameters. Okay, so you have to compromise with either one or two to get the other one or two parameters in terms of size, speed and power. So as I told, the smaller size is constants. For example, I will give an example. Like say for example, you are designing a RF tablet, right? So in a RF tablet, it is a very challenging chip actually, which is basically is used for the diagnosis of your intestine. Uh, this is just a small circuit, and it is encapsulated as a tablet, which is taken through the oral, and it will go through the all small intestine, long intestine, then it will come out. So where it is no, your chip size should be like a one tablet, right? It should not be bigger, and it should contain a all kind of circuits, including your camera as a sensor, uh, and it has to be transmitted to the outside. So it should have some RF circuits which will be embedded with RF circuit with your processor, and with the sensing part is your camera. It should be included, and that should be the size of the one tablet. So all the circuits you have to accommodate with a silicon, with a very small size silicon, so that it can be the size of your one tablet after packaging. So if you look at that, uh, uh, this smaller size, So if you look at the RF tablet, it needs a small size. Speed, obviously, speed is not that much important because it will go slowly and the signal is very, slow. So you can have a very low speed. But if you come to the, low power, because it has to be stay in the intestine, it has to pass through your intestine. It will take a long time, and since this circuit will be operated obviously through the battery, so battery life should be longer, so that it can, it can operate till coming into the intestine and coming out of the intestine, right? So this I mean that your, I mean, battery power, the which the battery you have to put it into your circuit, that should have a limited power, and only that you have to maintain that to to get that constant power, which is a fixed, constant mean that is fixed power with the battery. So that other side you have to, your circuit should consume the low power, right? So it is mandatory that your circuit should be consumes less power, so that it can be managed with the low power battery, which is embedded with your circuit, right? So if you look at this RF tablet, this is a good example. If you look at the RF tablet, so size is a challenge to design. And power is also a challenge to design, you have to look at. But the speed, okay, speed you can manage, that is third dimensions, you can manage it. But you cannot avoid the size, you cannot have a power. So this size and power will be hard constraint for the application, and to design a RF tablet for biomedical applications, right? So this is one example. And but sometimes, where the power is available, readily available from other source, then power is not a big issue. And maybe speed will be a big issue, particularly in communication systems when you go for the designing a communication modems. Okay, so that depends upon the applications. You have to this particular the size, speed, and power. Some of them will be hard constants, and so that some of them will be soft constants. So accordingly, you have to design your circuits, right? So when I talk about this, that you have to define the what should be the, as I told, that size of the chip means it should be a capsule size. So maybe some, few to the few size it will be. You have to accommodate your circuit within a few size, or maybe fractional of the centimeter squares. And similarly, power also, that depending upon, it should be a very low power in the range of say microwatt or picowatt. You have to look at that as a constant. You have to think about it. And the speed of, obviously it is a low speed. You can operate it uh, uh, at a low speed, but depends upon. So you have to set based on your applications. You have to set that, okay, my size, the chip, my size of the chip should be this much, and the power should consume this much, and speed should be this much. So size, speed, and power should be given as a constants, taken as a constants for your circuit design. So then now come to the as I was talking about. So this is the main objective and challenges and constants you will get in your design step of your VLSI. Okay, so if you look at that VLSI design methodology, let's come to the VLSI design methodology. There are two types of methods you have to you have to see. That is called a full custom design and semi-custom design. As I told, that full custom design is the this is the design methodology to customize your circuit or customize your design to fulfill your desired specifications. Say for example, if your circuit has to be operated at 100 megahertz, then you have to design your circuit such that it will give you the 100 megahertz. So you are customizing fully to satisfy your all the desired specifications. But in case of semi-custom design, in semi-custom design methodology, that you have to follow your design steps so that it may or may not meet your specifications. Say for example, your target specification is 100 megahertz. Like in terms of speed, it should work at 100 megahertz. When you follow this semi-custom design approach, your circuit may not operate at 100 megahertz. May operate also at 100 megahertz, but not always. Not always. It may operate at 98 megahertz or 99 megahertz or 101 megahertz or 102 megahertz. So it is close to your specifications, not equal to your specifications. So you may achieve also same specification if you will go with the semi-custom, but it is not always. So this is the way we have to study that full custom design methodology and semi-custom design methodology we will cover in this EE 309 course. So let's first we will go with the full custom design methodology, then we will come to our semi-custom design methodologies. So if you come to the full custom design method, we'll go to the full custom design method. Full custom design method. Okay. So in the first step, that you have to see what is your specifications. Okay. So if you look at the steps, follow the steps. So this is your, first step is your specifications. Specification. Then after the specifications, you have to do your circuit design. Circuit design means you have to design, you have to get your circuit topology. Okay, you have to get your circuit topology design, you have to do it, right? Or you have to get your circuit topology. Now, once it is done, your circuit part is done it, then you have to go for the next circuit verifications. So circuit simulation and verification. Circuit simulation and verifications. When you're talking about a circuit simulation and verifications, if it is a small circuit, okay, you can do manually, but it is a bigger circuit, it is not possible to do with the manually. You cannot do the verification manually. So obviously you have to go for your tool. You have to use a software, and that is called a electronics design automation tool, which is used for that both design and verifications, which will be used to design your circuit and simulation and verifications. So if it is a smaller circuit, so circuit you can do by hand and pen and paper, both to design and simulation and verification. But it is a larger circuit, it is not possible. If it is complex, then it is not possible to do the manual design and manual simulation and verifications. So you have to take the help of the tool that is called a EDA tool. EDA tool or EDA software, that is called your electronic design automation tool or electronic design automation software. So once it will done the simulation and verifications, then you have to go for the next step. That next step, that is called your layout design. Layout design. So in the layout design, so see in the first step when you're talking circuit design, you got your schematic design. Basically in the circuit design steps, you have a schematic design, right? And when you come to the layout design, you have to go to the next step, that is called a layout design. Layout design means that you have to get your physical dimensions of your transistors. Because when talk about the transistors, like talk about the bipolar junction transistors or MOSFETs, say bipolar junction transistors have a emitter region, base region, and collector region, right? And it's contact points to get your terminal out. Similarly, if you look at the MOSFET transistors, MOS transistors or MOSFETs, it will have a three main regions, that is source, drain, and gate regions, right? Of course, there are many these source regions, drain regions, and the gate regions are having a some physical dimensions are having with the different materials, right? So it has a particular dimensions. So based on the dimensions of the source, drain, and gate, your circuit performance will be you will achieve your circuit performance accordingly. So that depends upon the dimensions or physical size of your transistors, right? Physical size of transistors. So if you look at that gate region, that is called your channel region. Depending upon your channel region, that is your channel. If you look at the channel, okay. So if you look at that your channel region, right? So this channel region is having its W, width, and length, right? So if you look at this W and L, that's width and the length. This W, this dimension of your channel will give you the circuit performance. And for example, you might have already studied the device uh, class, that just to introduce that ID. So suppose if you look at the ID equations, right? ID equations, that is your mu n co x w by l, right? And that is your other parameters, voltage parameters, that is VGS minus VTHN, right? So this is saturation region, and similarly you will get further linear regions. So this characteristics of the MOSFETs or the performance of your MOSFETs will depends upon the drain current. Drain current is particularly depends upon the size of your MOSFET, that is your aspect ratio of your MOSFET, that is your W by L. So depends upon the size of the MOSFET, your drain current will vary, or characteristics of your circuit will be vary. So that is what I'm talking about. That then you have to go for then you have to go for your appropriate layout design to get your appropriate dimension of your transistors. Not only the transistors, also you should have a appropriate dimension of your interconnections also. Interconnections means that interconnections. So interconnections means that interconnections you have to do with the metal layers. So each metal layer, because when you use the metal layers, that metal layers will have its own resistance and capacitance. So depending upon the resistance and capacitance, your interconnection delay will be varied. So and obviously that size also matters. So you have to have a appropriate metal layers for the interconnections for your circuit. So it is necessarily to go for the layout design with specific dimensions of your devices or components or transistors and your interconnections. So you have to go for the next step, that is called a layout design. Means physical design and physical to get your physical dimensions of your components and interconnections. That is the step called your layout designs. Once layout design is done, uh, the next step is your next step is your uh, next step is your physical verifications. Means that you have to design that each layer and size of the each layer and uh, and overlapping of each layer, and is there any short circuit or shorting or it is open. So the physical verification means it will do the verification of the physical parameters of certain design rules, like this should be, because the circuit will be designed based on the some rules, that the minimum width of a particular metal layer or minimum overlapping of a particular metal layer. Okay, all these metal layers it will verify it. That is called a, in this step, in physical verification step, you have to go with your DRC, that is called a design rule check, and it will check the rules that is provided by your fabrication people to get your dimensions of your each layer. We will come to this, what is the design rules in detail, uh, how it comes up and what is the physical significance of these things. We will discuss it. Let me introduce the steps, then we will go each steps in detail. Then after DRC, you have to go for the another physical verification, that is called a LVS, that is called a layout versus schematic. Okay, layout versus schematic. I mean that what is the layout design you did it, that should be same as your what schematic you have, right? You have, so both schematic and the layout should be matched, so that you can say that your circuit is okay at the layout level. Then after that you have to go for the other checks like ERC. ERC, that is called a electrical rule check. So it will check some electrical rules like voltage drop and the current density. All these things it will check in a ERC. Uh, so then also in physical verification, sometimes we do the signal integrity issue, that to check the, as I told that again in the voltage drop or interference between the two metal layers, right? Uh, that coupling part will take care in electrical coupling, the coupling effect of your different layers, because layers he has to be put in very close to each other. So you have to look at the coupling effect of your circuit. So that will come under the signal integrity part. And another part is there is a more detail, you can say antenna check. Antenna check. That is also another physical verification stops. You have to check it. Antenna means that sometimes when you do the layout connection, some metal layers will be floating, and that will be treated as an antenna. So it will lead to a uh, bad performance of your circuit. So all these some of the verifications stops. You have to look at the physical verification step. Once physical verification steps done, then you have to uh, you have to go with you have to go with a, uh, step that is called uh, parasitic extraction. Parasitic extraction step. The parasitic extraction step is that uh, you know uh, uh, parasitic extraction is that uh, it will extract the unwanted components. Like suppose if you are realizing MOSFETs, so in addition to your ideal MOSFETs, you will get some resistors, some capacitors, some even bipolar transistors in addition to your MOSFETs. So you are expecting that you will get ideal MOSFETs, but when you go to the silicon realizations, you will get your some undesirable components, passive components, like passive and active components such as resistors, capacitors, and bipolar junction diodes, and also your transistors, bipolar transistors, which will have a bad performance on your ideal CMOS circuits or ideal MOS circuits. Okay, so that things that you have to extract the parasitics, the unwanted circuit component associated with your desired circuit, and you have to study how it will be how it will affect in your desired outputs. So those things you have to do. So you have to extract the unwanted circuits in your desired circuits. Okay, so that is a parasitic extractions. Once you do the parasitic extractions, you have to do the simulation after that. That is called a Back annotation simulations. Back annotation annotation simulation. So in the back annotation simulation, uh, what it does, I mean, as I told that once it is extracted the parasitics from your in your circuit along with your desired circuit and parasitic circuits, you have to simulate it and you have to verify your circuit, and that step is called your back annotation simulation and verifications. Means that you are extracting parasitics and you are back annotating these parasitic components with your original circuit part which one you have designed in the initial stage. Okay, and then you have to find out its performance, whether it is working as ideal to your desired specifications, right? So because parasitic components may affect your circuit performance, right, may affect your circuit performance, but not always. Obviously it will affect sometimes it is a tolerable also. So but still you have to check it. That is called your back annotation simulation and verifications. The next, once it is done, the back annotation simulations, right? So next step, you have to go for okay. You have to go for chip level uh, design, that integration with integration integ integration integration with pad. IO pad. IO pad. Okay. So see, before going to the IO pad, what is IO pad? Basically, if you look at the circuit view, I mean chip view of your circuit, then it is your core. Okay, so where you can have transistors are connected. Okay, like this. So you have a circuits, transistors, and this is a core, and you have to integrate with your IO pad. IO pad. IO pad, where it will have a ring, and these are the what is the block box I am writing. These are all IO input IO pad, and that will be used and connected to your physical pins of your chip. Physical pins of your chip. So these are all called your IO. Sorry, already then this is all called your IO pad. IO pad. So it is a IO ring, or each block is a IO pad. IO pad is a basically a simply metal layer. It is a simply metal layer sometimes, but sometimes it includes the other circuit, other protection circuit, and those protection circuit we will study. I will introduce those protection circuit, how the IO, how it is incorporated IO pad, and why we are incorporating in a IO pad. Okay, so this is a look of your VLSI chip at a design step. Okay, so you have a core, and you will have your IO pads. So that integration with the IO pad, you have to check it, and the next you have to once it is done it, then chip level verifications you have to do it. Chip level verifications you have to do it, and the next, once it is done, it is verified, then you have to generate, you have to generate a you have to generate a GDS to generate GDS, that is called a GDS file, that is called a geometrical data stream. Geometric.
Sir?
Yes.
Sir, actually the DSP classes started.
Okay. So then you go to the next class. Okay, we will discuss tomorrow. Okay.
Okay, sir.
Okay.
Thank you, sir.
Let's stop here, and then we will go to the next class.